dawn, a new eye on the universe. Welcome, cosmic explorers, to a journey that transcends time and space, a quest to unlock the universe's most profound secrets. For centuries, humanity has gazed at the night sky, captivated by its beauty and mysteries. But our vision has always been limited, obscured by the very fabric of the cosmos. Now, a revolutionary instrument has pierced through the veil, offering an unprecedented glimpse into the universe's earliest moments. The James Webb Space Telescope. This magnificent feat of engineering isn't just a telescope, it's a time machine, designed to observe the faint, stretched-out light from the first stars and galaxies that ignited after the Big Bang. Imagine looking back billions of years, witnessing the very infancy of the cosmos, understanding how the universe evolved into the breathtaking tapestry we see today. The Webb telescope is pushing the boundaries of human knowledge, allowing us to ask fundamental questions about our origins and our place in the vastness of space. Its primary mission is to explore the first light and reionization, the assembly of galaxies, the birth of stars and protoplanetary systems, and exoplanets. It's an observatory with capabilities far beyond any predecessor, primarily due to its massive mirror and its ability to observe in infrared light, which is crucial for seeing through dust and observing distant, red-shifted objects. The sheer scale of this endeavor represents the pinnacle of international scientific collaboration and human ingenuity, a testament to our insatiable curiosity about the universe. The very notion of seeing back to when the first stars were forming is truly mind-boggling, and Webb is delivering on that promise. The genesis of Webb. A vision takes shape. The James Webb Space Telescope wasn't born overnight. Its origins trace back to the ambitious aspirations of scientists in the late 1980s, who envisioned a successor to the Hubble Space Telescope, a telescope that could peer even deeper into the cosmos. Initially known as the Next Generation Space Telescope, NGST, the project underwent decades of rigorous planning, design, and construction. It was renamed in 2002 after James E. Webb, who was the second administrator of NASA and played a pivotal role in the Apollo program. The sheer complexity of Webb's design is staggering. Unlike Hubble, which observes primarily in visible and ultraviolet light, Webb is an infrared observatory. This critical difference allows it to penetrate the thick cosmic dust clouds that obscure visible light, revealing hidden stellar nurseries and the distant ancient light of early galaxies. The telescope's massive segmented primary mirror, spanning 6.5 meters, is composed of 18 hexagonal, gold-coated beryllium segments. This gold coating enhances its reflectivity to infrared light, making it incredibly sensitive. Each segment had to be precisely polished and aligned to an accuracy of nanometers, a task that required unprecedented engineering precision. The journey from concept to launch was a marathon, fraught with technological challenges, budget overruns, and scheduling delays. Yet, the scientific community's unwavering belief in its potential propelled the project forward. It became a testament to human perseverance and the collaborative spirit of international space agencies, primarily NASA, ESA, European Space Agency, and CSA, Canadian Space Agency, working together towards a common goal of scientific discovery. The need for power. Why Hubble wasn't enough. For over 3 decades, the Hubble Space Telescope has been our cosmic ambassador, delivering breathtaking images and profound insights into the universe. It revolutionized our understanding of galaxies, stars, and even the expansion of the universe. So, why did we need an even more powerful telescope? The answer lies in the fundamental nature of light and the expanding universe. As light travels across billions of light years, the expansion of space stretches its wavelengths, causing visible light from distant objects to shift into the infrared spectrum, a phenomenon known as cosmological redshift. Hubble, primarily a visible and ultraviolet light telescope, simply couldn't see these deeply redshifted objects. It was like trying to hear a whisper across a stadium. The signal was too faint and distorted. The early universe, filled with the first stars and galaxies, is shrouded in a dense fog of hydrogen gas and cosmic dust, impenetrable to visible light. Webb's infrared capabilities are its superpower, allowing it to cut through this cosmic haze, much like night vision goggles see in the dark. Moreover, Webb's mirror is significantly larger than Hubble's, 6.5 meters versus 2.4 meters, collecting far more light and enabling it to detect fainter, more distant objects. Its colder operating temperature, maintained by a tennis court-sized sunshield, minimizes its own infrared emissions, crucial for detecting the incredibly faint infrared signals from the early universe. Without these advancements, the earliest chapters of cosmic history would remain forever out of our reach, a tantalizing mystery that Hubble could only hint at. The launch and journey, a leap of faith. On Christmas Day, December 25th, 2021, the world held its breath as the James Webb Space Telescope embarked on its perilous journey into the cosmos. Aboard an Ariane 5 rocket, a workhorse of European spaceflight, Webb roared into the sky from Europe's spaceport in Kourou, French Guiana. This launch wasn't just another rocket ascent. It was the culmination of decades of dreams, billions of dollars, and the dedication of thousands of scientists and engineers. Every moment of the launch was critical, as Webb was a single-shot mission. There would be no opportunities for repairs or adjustments once it reached its distant orbital destination. The journey to its operational orbit, nearly 1.5 million kilometers, about 930,000 miles, from Earth at the second Lagrange point, L2, was a complex ballet of engineering. Unlike Hubble, which orbits Earth, L2 offers a stable gravitational environment, allowing Webb to maintain a precise orientation relative to the Sun, Earth, and Moon, and crucially, keeping its delicate instruments perpetually shielded from their heat and light. The most nail-biting part of its journey was the 29-day deployment sequence. Webb was too large to fit into any rocket in its fully assembled state, so it was launched folded up like a piece of origami. Its massive sunshield, designed to cool the telescope to nearly absolute zero, meticulously unfolded in space, followed by the deployment of its secondary and primary mirrors. Each step was a high-stakes maneuver, with countless single points of failure. The success of this deployment sequence was nothing short of miraculous, a testament to the extraordinary precision and foresight of its creators. Unveiling the first light, a glimpse of infancy. One of the primary scientific goals of the James Webb Space Telescope is to witness the first light, the dawn of the universe, when the very first stars and galaxies began to form after the Big Bang. For billions of years, the universe was a dark, opaque soup of hydrogen and helium, known as the cosmic dark ages. It was only when gravity coalesced these primordial gases into the first massive stars that light finally broke through the cosmic gloom. These early stars and their subsequent supernovae then ionized the universe, clearing away the opaque gas and making it transparent to light. Webb's incredible sensitivity to infrared light allows it to capture the faint, red-shifted glow of these pioneering celestial objects. Its deep field images are a revelation, pushing the boundaries of what we thought was observable. We are now seeing galaxies that existed just a few 100 million years after the Big Bang, appearing as faint, reddish smudges in Webb's imagery. These embryonic galaxies are surprisingly bright and numerous, challenging some of our previous models of early galaxy formation. Scientists are analyzing their light to understand their composition, their star formation rates, and how they contributed to the ionization of the universe. This is not just about seeing distant objects. It's about understanding the fundamental processes that shape the cosmos, tracing the lineage of galaxies like our own Milky Way, back to their earliest ancestors. It's truly a journey back to the universe's infancy, revealing the very foundations upon which all subsequent cosmic evolution was built. The Dance of Galaxies, Cosmic Evolution in Action. Beyond the earliest galaxies, Webb is revolutionizing our understanding of how galaxies evolve over cosmic time. Galaxies are not static entities. They are dynamic, ever-changing systems that grow, merge, and interact with one another. Webb's unparalleled infrared vision allows us to peer through the thick dust clouds that often obscure the visible light from star-forming regions within galaxies and their active galactic nuclei, AGN. We are seeing intricate details of galactic mergers, where two colossal systems collide and eventually combine, triggering bursts of star formation and reshaping their structures. These cosmic collisions were particularly common in the early universe and played a crucial role in the growth of massive galaxies. Webb's observations are providing unprecedented insights into the life cycles of galaxies, from their turbulent birthplaces to their majestic maturity. It's allowing us to study the distribution of gas and dust within galaxies with exquisite detail, revealing the intricate nurseries where new stars are being born. By observing galaxies at different stages of their evolution, from those near the cosmic dawn to those resembling modern galaxies, scientists can piece together a comprehensive timeline of galactic development. This includes understanding the role of supermassive black holes at the centers of galaxies and how their activity influences the star formation and evolution of their host galaxies, offering a more complete picture of the universe's grand evolutionary narrative. Star birth and planet formation, from dust to worlds. The James Webb Space Telescope is also fundamentally changing our understanding of how stars are born and how planets form around them. Stellar nurseries, vast clouds of gas and dust, are the cauldrons where new suns ignite. However, these nurseries are often opaque to visible light, making it difficult to observe the nascent stars and their surrounding protoplanetary disks, the swirling cocoons of material from which planets eventually coalesce. Webb's infrared eyes effortlessly penetrate these dusty veils, revealing stunning details of these cosmic birthplaces. We are seeing young protostars still shrouded in their cocoons, jets of material streaming from them, and the intricate structures of protoplanetary disks, where the building blocks of planets are actively forming. The level of detail in these images is unprecedented, allowing astronomers to study the chemical composition of these disks, identify the presence of water ice and organic molecules, the very ingredients for life, and even detect gaps and rings within the disks that suggest the presence of forming exoplanets. These observations are providing direct evidence for the theories of planet formation, helping us understand the processes that led to the creation of our own solar system and countless others throughout the galaxy. It's like having an ultrasound of a cosmic womb, witnessing the miraculous gestation of stars and planets in real time. Exoplanets, the search for other Earths. Perhaps one of the most exciting frontiers for the James Webb Space Telescope is the study of exoplanets, planets orbiting stars beyond our Sun. The discovery of thousands of these distant worlds has ignited humanity's ancient question: are we alone? Webb is not only finding new exoplanets, but more importantly, it's scrutinizing their atmospheres with incredible precision. When an exoplanet passes in front of its host star, a transit, a tiny fraction of the star's light filters through the planet's atmosphere. Webb's instruments can analyze this filtered light, breaking it down into its constituent colors, a spectrum, to reveal the chemical fingerprints of various molecules: water vapor, methane, carbon dioxide, and potentially even signs of biological activity. This capability is a game changer in the search for habitable worlds. Already, Webb has delivered groundbreaking results, detecting water vapor in the atmosphere of several exoplanets and even hints of other molecules. It's helping us understand the diversity of exoplanetary atmospheres, their temperatures, pressures, and compositions, providing crucial clues about their potential to harbor life. While Webb isn't designed to directly detect life, it can identify biosignatures, chemical imbalances, in an atmosphere that might indicate the presence of living organisms. This is a monumental step forward in our quest to find another Earth, or perhaps discover life in forms we can barely imagine, pushing the boundaries of astrobiology and our understanding of life's cosmic potential. The unforeseen discoveries, surprises from the cosmos. While the James Webb Space Telescope was designed with specific scientific objectives in mind, the history of astronomy teaches us that the most profound discoveries often come from the unexpected. Webb is already delivering on this promise, unveiling phenomena and challenging existing theories in ways we hadn't anticipated. For example, the sheer abundance and brightness of very early galaxies observed by Webb have surprised astronomers, suggesting that star formation in the early universe might have been more efficient than previously thought. This is forcing scientists to re-evaluate their models of cosmic evolution. We are seeing details within nebulae and star-forming regions that reveal complex interactions between young stars and their environments, providing new insights into how stellar winds and radiation sculpt these cosmic landscapes. In the realm of exoplanets, some atmospheric compositions are turning out to be more complex or unusual than theoretical models predicted, hinting at new chemical processes or planetary formation pathways. Webb's ability to see in unprecedented detail and sensitivity is revealing a universe far richer and more intricate than we ever imagined. These unforeseen discoveries are a testament to the power of pushing the boundaries of observational technology. They remind us that the universe always holds surprises, constantly pushing us to refine our understanding and expand our scientific horizons. The true beauty of a groundbreaking observatory like Webb lies not only in confirming existing theories, but in opening entirely new avenues of inquiry, sparking new questions, and inspiring future generations of scientists to continue exploring the unknown. The legacy of Webb, a new era of exploration. The James Webb Space Telescope is more than just a scientific instrument. It is a symbol of humanity's insatiable curiosity, our relentless pursuit of knowledge, and our collective dream to understand our place in the cosmos. Its journey from a visionary concept to a fully operational observatory, delivering groundbreaking discoveries, represents a triumph of international collaboration, technological innovation, and sheer human determination. The images and data pouring back from Webb are not just for scientists, they are for all of humanity. They are inspiring a new generation of astronomers, engineers, and dreamers, reminding us of the infinite wonders that await discovery. Webb's legacy will extend far beyond its operational lifetime. The data it collects will be analyzed for decades, revealing countless new insights and shaping our understanding of the universe for generations to come. It will serve as a benchmark for future space telescopes, pushing the boundaries of what is possible. From witnessing the universe's first light to scrutinizing the atmospheres of distant exoplanets, Webb is fundamentally rewriting our cosmic story. It is revealing a universe that is both more ancient and more dynamic, more intricate and more diverse than we ever conceived. As we continue to gaze at the universe through Webb's golden eye, we are not just seeing light, we are seeing time, we are seeing creation, and we are seeing the boundless potential of human exploration. The universe is calling, and Webb is answering.